Welcome to the course on Fundamentals of MIMO Wireless Communication. Today we are in lecture number 3, where we will talk about overview of MIMO communication systems. In the previous lectures, we have seen till now how wireless communication has emerged from 1960s, starting with the Maxwell's equation. Then we have seen how systems have grown from the first generation to the fifth generation system. One of the important things that we may have noted is that between first to fourth generation systems, one of the most important drivers of growth has been high bit rate requirement. Along with that, especially in the fourth generation systems, there was requirement to support high mobility. Whereas when we looked at the fifth generation communication systems that are currently being designed, we saw that there is a diverse set of requirements, which does not necessarily be in the direction of increase of data rate. Increase in data rate is definitely one of the means, but there are many other requirements which have come up. We have also seen some of the important assumptions on digital communication systems that we need to make while undergoing this particular course. One of the first assumptions we talked about was it requires ideal frequency synchronization. The second important assumption we made is that it requires ideal timing synchronization. That means there is no inter-symbol interference. The third important assumption we made is that there should be perfect channel estimates available at the receiver, so that there is no error due to channel estimation, so that we can concentrate mainly on the signal processing algorithms and performance analysis of systems based on ideal conditions. We have also seen what is known as the radio access network, where we have been discussing about the last part, which is containing of the transmitter and the access point, and we have looked at wireless systems in this part. We have also identified which is the core network. In this course, we will be mainly concerned with this access part of the network. Moving ahead, just to summarize, we know the 7 OSI layers, starting with the physical layer. Then above that there is data link layer or MAC layer. Then there is the network layer, transport layer, session layer, presentation layer, and application layer. In the application layer, you are well aware of things like HTTP, FTP, SMTP, and so on. In the presentation layer, it's mainly to do with data formatting like JPEG, etc. Then there is the session layer, which controls session between communication systems. Transport layer is usually there to maintain quality of service between end-to-end devices, and network layer is there to route a packet from the source to the destination going through different nodes in the network. The data link layer, or also sometimes referred to as the MAC layer, is critical in controlling the link parameters or access to the medium. Finally, there is the physical layer, which is the lowest layer and which interacts directly with the medium. In this particular course, we will be concerned in the lower two layers, or primarily we will be looking at the physical layer and also some parts of the data link layer or the lower MAC layer. Especially we term the work in these areas as cross layer designs. Most modern communication systems are using advantage or knowledge of the physical layer in the higher layers, so that they can adapt their transmissions so as to achieve a reliable communication link, as well as to reduce the delay between the transmission and the reception. Now we take a look at a typical block diagram of a digital communication receiver. So we have the source at the input. The source at the input, if it is an analog input, usually goes through a sampler, followed by the quantizer, followed by source encoding, examples which do compression of the source. One possible could be image compression algorithms. This whole block is usually termed as source signal processing, or also sometimes referred to as source encoding. This is in some systems followed by a scrambler. Scrambler is usually present to mix up the sequence of ones and zeros, so that it avoids long sequence of ones and zeros that helps in achieving synchronization at the receiver. In some systems you will find a cyclic redundancy check being present, which helps in checking whether a packet is being received correctly or not. Followed by the CRC check, there is the forward error correction module and an interleaver. At the output of the interleaver is fed to in digital communication systems something known as the symbol mapper, which the output of which is further put into pulse shaping, which may be further fed into a D2A converter, and then may or may not be presence of an IF stage, followed by the RF stage, which includes up conversion and a spectral mask, followed by an antenna or a corresponding transducer depending upon the medium. This is a typical block diagram of a transmitter. In case of MIMO communication systems, this particular section is rather replicated to transmit signal across multiple antennas, which we will see very shortly. On the receiver front, the antenna receives the signal, followed by the RF section, which includes a low noise amplifier, followed by a band pass filter, followed by a down converter through a mixer into either the IF stage or to the baseband stage, depends upon the kind of mixer and the particular specific communication system at hand, followed by the sampler or A to D converter. This will also vary depending upon the particular communication system, because there could be matched filter represented or utilized in the digital domain, or it could be in the analog domain. Then there would be the timing synchronization, which would include packet sync. The packet synchronization is important in some systems where burst mode communication is present. From the packet sync, they could be going into frame sync. Packet sync is sometimes also referred to as packet detection, which simply detects the presence of a packet or non-presence of a packet. Followed by the packet detection, there is a frame synchronization, which identifies the exact start of a packet, which is followed by the carrier synchronization, sometimes there is iteration between carrier sync and frame synchronization. This carrier synchronization, after carrier synchronization, there would be the channel estimation equalization block as we had shown in the previous diagram, but before that there would be the clock synchronization, followed by the clock sync. There is, we will make one module, channel estimation, and equalization. After we have the channel estimation equalization, there could be an important module known as combiner. Now, typically when we talk about combiners, these combiners are generally mentioned for communication systems such as CDMA, whereas when we talk about MIMO, these combiners could be related to the combining of signals arriving through multiple antenna ports or multiple antenna chains. So, once we are through with the combiner, then there would be the decision logic for the baseband processing or the demapper. This could be hard decision or this could be soft decision. From the demapper, it goes into the de-interleaver, followed by decoder of the FEC, followed by cyclic redundancy check at the receiver, which checks whether the redundancy added is received intact, so that it can identify the packet received is correct or not, followed by the opposite part. What is done at the transmitter is the descrambler, which is usually done using a seeded random sequence, and then passed on to the, I will make a large block for the source decoder, which would include the corresponding block of the source encoding. Corresponding to source encoding, there would be source decoding, hence from the compression it is going to extract the information. Table lookup for quantizer, there should be a corresponding table lookup, followed by D2A as may be necessary. So, this way we can build up the entire block diagram of the transmitter and the receiver. Now, we can clearly see that if we compare block diagrammatic representation of the transmitter and receiver, the receiver has many more components than the transmitter, and some of the important components which are additional at the receiver are the synchronization modules, the timing synchronization modules, the frequency synchronization modules, the clock synchronization modules, the channel estimation equalization modules, the combiner modules. These are additional on top of what is present at the transmitter, and hence designing of the receiver is very critical. And what we can see also from the figure, that between the transmitter and the receiver there lies the channel. The design of the transmitter is usually done in such a way so that the signals which are coming out from this section are matched to the channel. The receiver is designed in such a way so that all the distortions which the channel introduces is resolved, so that when the signal following through all this process finally comes at the destination, it is with minimum errors compared to any other situation. If all these blocks were not present, there will be huge amount of errors because of the channel. As we move on with this background that is already discussed, we will now take an overview of MIMO communication systems, trying to see how typical MIMO communication architectures are present, which will give us an overview of what we are going to cover in details in this particular course. When we talk about MIMO, what we mean is we have the transmitter, which encompasses all the blocks that we have already described in the previous diagram. Instead of one antenna, what we have described in the previous figure, there are multiple transmitting antennas. Typically, in many references, they will be referred to using NT. These signals are sent simultaneously from these antennas and they propagate through the channel. So, instead of one transmit antenna, one receive antenna, there would be multiple transmit antennas and there would be multiple receive antennas. At the receiver, there will be multiple signals which is received and processed instead of a single antenna signal, partly of what we have already described. In a typical seesaw link, the received signal Y, which is mentioned over here, can be represented as Y equals to H times X, where X is the transmitted baseband signal, and this is what we have discussed in the earlier class, that we will not talk about carriers. So, we are talking about baseband signal plus noise. Noise is what is due to receiver components, and H represents the channel. Typically, you may have studied about convolution, but this is the simplest form of relationship if it is a non-convolving channel or a flat fading channel. For MIMO links, on the contrary, what we have is we have XM, M going from 1 to NT, that means X1, X2, X3 up to XNT, each getting multiplied by HM, and then at being received at, let us say, antenna Y1. So, if I take Y1, this is equal to sum over all the links that are present, all the transmitted signal multiplied by the corresponding channel links, and this will be for Yn equals to 1 to NR. So, we will be getting several such signals. Once we get several such signals, we have to process them at the receiver, so that our end goal is we will be able to extract the signals that are being sent from the transmitter. If we look at the benefits from multiple antennas, the first important benefit that we gain from multiple antenna transmission is known as diversity gain. When we talk about diversity gain, it helps us overcome small scale fading, details of which we are going to see very soon. And the next important benefit of spatial diversity combining is path loss. That means, if there is arrays of antennas that are present at the receiver, so they will be used to combine the strength of the signals, so that there is average increase in SNR. We will discuss all these in details. So, when we talk about the diversity gain, what we mean is, suppose I have a signal which is coming in this form, and we have another signal which comes in this way. So, by diversity combining, what we mean, we will of course see in details later, is at any one instant of time, if we consider this time, since we have 1 and 2 copies of signal, either of these two signals will be above a certain threshold. Whereas, if we would have taken only one, there would be instances when one of the signals is below a threshold or when the other is below the threshold. So, that is the advantage of diversity combining. Whereas, if we look at the array gain, there what is being done is the signal that is received from one of the antennas and the signal which is being received by the other antennas, they are all combined in such a way that whereas each signal was arriving at different SNR values, after combining, the combined SNR can be at a much higher level, and we get an increase in average signal strength, thereby improving the performance of these communication systems. If we take a look at the second important gain which MIMO provides, that is with increase in capacity. That means, this is achieved through something known as spatial multiplexing, which we will again see very shortly. So, as the name suggests, there is multiplexing that is going on. So, multiplexing means simultaneously or mixing up several serial streams so that they can go together. So, there is parallel stream transmission. That means, at the same time using multiple antennas, it can send to more than one user, or even to one user it can send two different data streams. The next important method of using multiple antennas is through beamforming, as is shown in this particular figure, that specific beams are formed which are very directional, and users can be present or addressed in each of the beams separately, and this would also help reduce interference. That means, if one user is radiating from this direction, another user is radiating from this direction, because of forming separate beams for these users, the interference from one user can easily be taken care of by forming these special beams. This is also can be used for space division, multiple access, and other techniques. If we look at the benefit that MIMO brings, is this is one diagrammatic representation of one of the results, which we will see of course later on. The x axis shows SNR in dB, the y axis shows average capacity in bits per second per hertz. Again, we will define all these terms. M equals to 1 means there is one transmit antenna, one receive antenna. Typically, this is a seesaw system, what we are usually used to. As we go to m equals to 2, that means we are going to this particular curve. That means there are two antennas at the transmitter, two antennas at the receiver. We see that as SNR increases, the spectral efficiency increases in such a fashion that compared to a seesaw link here, the SNR increase is significant. As we move to the next one, which is m equals to 3 or a 3 cross 3 system, then we get another significant jump. And then when we move to a 4 cross 4 system or 4 transmitters and 4 receive antennas, we reach here. So, apparently what we see, there is approximately a linear increase in capacity or linear increase in spectral efficiency as we increase the number of antennas from 1 to 2 to 3 2 and 4. So, this is one of the biggest gains that MIMO brings to us, and in this course we are going to study how we are going to achieve these particular gains. If we take a look at how MIMO is used in commercial systems, for example LTE or others, MIMO antenna systems can be broken down into one of the sub cases: seesaw, single antenna single output; CMO, single input multiple output, that is one transmit antenna multiple receive antenna; multiple input antennas, single output antennas; and finally multiple input multiple output. MIMO systems can provide us with diversity gain and spatial multiplexing gain, as we have discussed. In spatial multiplexing, we have single user and multi-user scenarios as well as dedicated beamforming. In single user scenario, we have open loop spatial multiplexing, closed loop spatial multiplexing. One of the objectives of this course is that we will cover these parts as highlighted in this particular slide. In this diagram, we will try to briefly discuss or tell the overview about what is single user MIMO. In single user MIMO, we have multiple antennas at the transmitter, multiple antennas at the receiver, and signals are all mixed up when it comes to the receiver. At the receiver, due to signal processing and due to pre-processing at the transmitter, it may be possible to create parallel interference free channels, thereby separate streams which do not interfere with each other may be possible to be transmitted from the source to the destination, and we will be able to receive separate interference free data streams at the receiver. One of the important objectives of this course is to understand how this can be realized and what capacity gains are achieved because of such processing. If we move further, if these receivers, instead of being connected together, if they are now separated, whereas at the transmitter the antennas are co-located, in that case what we have is a multi-user MIMO. So, these will be multiple users and this will be the base station, for example. In this mode, the transmitter would be able to send separate streams to user 1, to user 2 and user 3 simultaneously using similar but improved signal processing algorithms. And when we move further, take an additional step at the transmitter, if we have these antennas now distributed so that they form parts of different antenna systems, and there are different receivers, whereas this source they are somehow connected to each other, what we have is a multi-point transmission to multiple users, which is one of the most complicated part of MIMO systems. Moving ahead further, we will take a brief look of how a typical communication systems work, then we will see what complexities MIMO adds to this system. An understanding of MIMO would help resolve designing these complex communication systems, design better algorithms at the transmitter and at the receiver. A typical communication system has experiences channel, which is described by this particular figure. Of course, we will spend significant time trying to understand. What we briefly see is that across time and frequency domain, there is fluctuation of signal strength across this whole space. We have a typical cellular structure where there might be base stations across at the central part of the nodes, and they would all be transmitting simultaneously. One of the central nodes over here is the base station, which connects to multiple users. They send beacon signals, the users send back channel quality indicator. At the base station, there is a cycle of events that happen, which include link adaptation, followed by packet scheduling in both transmit and frequency domain. There is transport block formation, there is QoS adjustment, there is beam forming, or there could be special multiplexing or diversity mode, there is call admission control and hybrid ARQ. So, all these process keeps on happening in one of the base stations, and this keeps on happening at all these base stations simultaneously. With the advent of MIMO, one extra processing comes in is selection amongst these different modes, and even when we go for multi-user MIMO, one has to select between multiple users. If we look at when this gets added, when the MIMO techniques which we briefly described get added to a typical large communication system, what happens is all the processing that we have discussed goes on at the base station of one of the cells, and there are other cells which are nearby, and in a typical multi-point transmission, these base station 1 and base station 2, they would typically communicate to one central processing unit, whereby base station 1, 2 and 3 for example would jointly send signals to these users in such a way that there is no interference from these, which apparently there is huge amount of interference, whereas there is a constructive generation of the signal, so that huge increase in spectral efficiency is achieved, outage is reduced, especially at the cell edge, which is otherwise not possible without the use of multiple antennas and coordination between these base stations. As we move further, the other forms of coordination could be that there are typical processing going on in the base stations, and these other base stations, they do not do joint processing, but there is communication amongst these base stations, but they send independent signals, but they do in such a way the selection of MIMO modes, which is also known as MIMO beam forming, is done in a coordinated fashion, so that they reduce interference, especially at the cell edge, thereby improving the quality of service. The other mode of coordination, which is known as coordinated scheduling and radio resource allocation, again these base stations do talk to each other, but they generally do not do joint signal processing, but through coordination they exchange information about the channel conditions, and they together solve the problem of allocating resources to users in this space who would be actually hearing to transmissions from all these neighboring base stations. They solve it in such a way so that the interference is reduced, resource allocation is maximized, and overall there is gain in the performance of the systems. Just last few minutes for today's lecture, where we talk about the prerequisites for this subject. So, as we have been discussing till now, we would require you to revise digital communications. We have briefly touched upon some of the concepts. We would require a lot of probability and statistics. So, your understanding of probability and statistics is important. Linear algebra is required to be revised. The books which we will follow, some of the books would be Wireless Communications by Rappaport, Principles of Mobile Communication by Gordon Stober. These ones will especially refer in the beginning part where we will talk about the channel. Introduction to Space-Time Wireless Communication by Pollaraj et al. Is one of the most important references which we are going to follow throughout when we will be talking about MIMO channels as well as MIMO signal processing. So, this is one of the important books to be followed. There are other books like Wireless Communication by Altria Goldsmith, Elements of Information Theory by Cover and Thomas, which will also be necessary. Below there is a list of a few important researchers in this domain who have been prolific authors. So, beyond the coursework, I would encourage you to go across and find even more authors in the domain of MIMO communications who have been producing rich literature, so that this domain has been improving, and we are at a stage where we are able to take it as a course. Other reference materials, if you do not limit yourselves to these materials, feel free to go into journals and conferences which keep on getting published to provide the latest results. Yeah. So, we stop at this particular point in the third lecture, and we will discuss some more things in the coming lecture, the fourth one. Thank you.